So welcome to the last part of lecture 10. So in this part, the main thing that I want to do is prove the fundamental theorem of linear maps. And so I stated it already that the dimension of V is going to be equal to the dimension of the null space of T plus the dimension of the range of T, where T is any linear map from V to W. So let's prove this. Okay, and you'll see some of the results that we've had before about like extending bases coming in handy here. So we start with a basis for our null space T, because null T is a subspace. It has a basis because V is finite dimensional. So we're just going to say that, oh, we have n elements, and we'll just say that implies that the dimension of the null space is n. So then, because u1 through un are linearly independent in V, we can extend this set to a basis of the whole vector space, right? So we extend it. So we have u1 up to un as the first element, and then I add in, and I'm not sure how many elements I have to add in, but let's call them v1 through vm. So this implies that the dimension of v is n plus m. So what we have is dimension of V is equal to the dimension of the null space plus this number M. Right? So there's kind of two things that we need to do to finish off the proof. We need to show that the range of T is finite dimensional. That was the first thing. And the second thing is we need to show that the dimension of the range is M. So this part here would be equal to the dimension of the range. We know the n is the dimension of the null space, and we've already connected it to the dimension of n. So those are the two things we need to do. So let's first show that the range of T is finitely dimensional. Okay, so we have a basis for V, U1 up to UN, and then V1 up to Vn. So that means that anytime I take a little vector V inside of my big space V, I can write it as a linear combination of these elements. So these are kind of elements coming from the basis of the null space plus the things that we extended it. So now we hit V with our linear map, right? Okay, we say, okay, I want to evaluate V at T. And what that means by the properties using both homogeneity and the additive property is that this is equal to A1 times TU1 up to AN times TUN plus B1 TV1 up to BM TVM. Okay, so I'm just taking T, applying it to both sides, and then I'm using the properties of a linear map. But the thing that you want to notice is that each of these guys, U1 up to UN, they're in the null space. So this is equal to 0. All of these guys are equal to 0. So you're only left up with is B1 times V1 up to BM up to TVM. So what we have is that the range, right? So TV is in the range. It has to be some sort of linear combination of these particular elements, TV1 up to TVM, right? So the range of T is going to be the span of these particular vectors. And now this actually gives us what we needed to, part of what we needed to do, right? So this implies range T is finite dimensional. Because remember, the definition of finite dimensional just says that your space can be spanned by a finite number of vectors. Okay, so now what we need to do is we need to show that TV1 up to TVM are linearly independent. So what we want to do now is basically show that not only do they span the whole space, but they're actually a basis. Okay, so what we wanted to do is show that these guys are linearly independent, and if that's true, we actually get the conclusion that we're looking for, right? Namely, that the dimension of the range of T is M. So we boil down our problem into showing that these vectors are linearly independent. Okay, so well, how do we do that? Well, we want to show that these vectors are linearly independent. So let's suppose that we have a combination of these vectors that equals 0. Now, using the properties of a linear map, we can kind of use the homogeneity and the additive property to kind of rewrite it as T evaluated at the vector C1 times V1 up to the vector CM VM, sending it equal to 0. So this vector equaling to 0 is the same thing as saying that the map T sends this vector to 0. Right? But this implies then that CV1 up to CMVM is in the null space of T, which we said at the beginning is the span of U1 up to UN, right? Because U1 to UN is the basis of my null space. Okay, so this means that this vector on the left-hand side can be written as a linear combination of the vectors on the right-hand side. So let me do that. Hence C1V1 up to CMVM is equal to D1U1 up to DNUN for some DI. But now look that you can rearrange this equation and you get C1V1 up to CMVN plus minus D1V1 up to minus DMVN. Oh, sorry, these should be U's. Let me rewrite that. And this is equal to 0, okay? But V1 up to VM combined with U1 to UN is a basis. But V1 VM, U1 UN is linearly independent. So each of these numbers, all of these coefficients have to be, and I guess these can be D's, we don't have to worry about the negative signs, they all have to be 0, okay? So in particular, C1 up to Cm is equal to 0, so TV1 up to TVM is linearly independent, which is what we wanted to show. Okay, so that finishes off the proof of the fundamental theorem of linear maps. So at this point, I would normally stop to see if people have questions, but since we're online here, I'll just keep going. And I will just kind of point out that this theorem, we'll go back over here, may look kind of familiar. And the reason it may look familiar is because we actually proved a special case of this in Math 1B03, where we learned about the rank nullity theorem. And the rank nullity theorem says that if A is an m by n matrix, then the rank of A plus the dimension of the null space of A is equal to n, right? And so this is equal to the dimension of the column space of A. And so why is it really just a special case of the fundamental theorem? Well, look what happens. If you give me a matrix, that matrix defines a linear map from Rn to Rm by taking a vector taking a vector x by sending that vector x to A times x, okay? So i.e. T is now in Rn to Rm. Okay, so now let's put all the pieces together. Then we know n, which is equal to the dimension of Rn, right, is equal to, well, it's going to be equal to the dimension of the null space of T plus the dimension of the range of T, right? So this is the fundamental theorem that we just proved. Fundamental theorem, because we're talking about a linear transformation. But now we want to kind of remember what these things mean when we're talking about matrices, right? This is equal to the dimension of the null space of your matrix A, and this, when you're looking at a map given by a matrix, this is going to be equal to the dimension of the column space of A. Okay, so this is kind of what we saw before in one of our previous examples, that the range of T corresponded to the dimension of a column space. And another way to think about this is the dimension of the null space of A plus the rank of A, because usually we call the rank of A the dimension of the column space of A. Or sorry, let me rephrase that. The rank of A denotes the dimension of the column space of A. So hiding kind of inside of this proof, right, is this one equals this one, but that's just the fundamental theorem of linear maps. And what's interesting is when we proved this in Math 1 BO3, we actually proved it by counting pivots inside of our matrix. And here we don't see any of that information about our matrix. We're actually using the fact that we have a linear transformation and keeping track of the various sizes of the various subspaces. Okay, so there was a lot of things that we learned today. The key ideas that I think that you want to take away from today's lecture are the null space of a transformation, linear map, the range of a linear map, and then the fundamental theorem of linear maps. Okay, all of these things are quite useful. So I think that's it for today. I hope you have a good day, and let's have a smiling guy wishing you a good day. Okay, and I'll see you in lecture 11. Bye.